So maybe you're thinking last lecture, why are we putting in all this effort to simplify roots when it just honestly makes them look slightly more complicated? And that's what we're going to build into it in this lecture. And so we talked about like terms before when we were dealing with variables, x squared versus like xy, when we can add them or subtract them, we can't. Very similar concept when we're dealing with roots. I can't add or subtract roots if they have different roots, or if what's under the root is different, or if the root is the same and what's under the root is different, or if everything's different. So really the only case that we can combine things is if we have the exact same root and the exact same value under the root. So obviously root 5 meets that category. I can have something in front of my root, that's okay. So I have cube root of 6, cube root of 6, and now I have a 4 in front of it. And now the last one looks like they're not the same, because it's 2 and square root of 2 and square root of 8. But if we go through the process of simplifying 8, it actually becomes 2 root 2, which makes them like terms. And so then I could add or subtract those radicals. So in the simple case, we have this, the roots are the same, the numbers are the same, and so we would just add the numbers in front, very similar to what we did with variables. We add those coefficients, and so 7 plus 5 is equal to 12, so 12 cube root 52. Now, if it's not the case, if I have root 6 and cube root of 6, well, those are pretty close, but the root numbers are different. That is actually no real solution. It's not the correct thing. This is an old PowerPoint. It would just does not simplify, is what we would say. I can't make my thing any nicer. Now, some cases we have these two roots and the numbers under them are not the same. Sure, the roots are the same, but the numbers under them are not. So it seems like the answer would be it does not simplify, but that's not true. What we have to do to make sure that we can claim that is we have to simplify our radicals as far as possible. So to simplify 24, I'm going to break that into 6 times 4 gets me 24, 2 times 3 gets me 6, 2 times 2 gets me 4, and now I have a pair of 2's that I could put in front of my root, and I have a 2 times 3. I have a 6 left behind. So my first root becomes 2 root 6. And now I do a very similar process for my second root. I don't really deal with the 3 right now. I'm only concerned what's under the square root, which is 54. 6 times 9 gets me 54. 2 times 3 gets me 6. 3 times 3 gets me 9. And so I have a pair of 3's here, and then I have, again, a 2 and a 3 left over. So in this case, I would pull a 3 out of my root, and I would be left with 2 times 3 gets me 6 under my root. And so I would have 3 times 3 root 6. Boy, I'm bad at keeping track of my numbers in front of my roots. So that second term should be 6 or 9 root 6, not 3 root 6. And so if that's the case, I would get 2 plus 9 would actually get me 11 root 6. So in this case, I guess just to make it so that it's not super duper confusing, we're going to neglect the 3 in front of that first set of roots. So I had 3 root 54. Let's pretend I was actually doing a problem of just root 54, because that would be easier to track. And so if I do that, then the rest of the problem falls out exactly how it is. I would put a 3 in front of my root. I would have 2 times 3 is equal to 6. And then I would get 5 root 6. Hopefully that wasn't super confusing. Imagine it might be, but the good news is we have another example coming right up. And so now I'm dealing with cube roots. Again, I'm going to go through, I guess I spoiled a little bit. I'm going to go through, oh, okay, I know what I did. So in the previous problem, we saw that I made my factor tree for 24. So I'm not going to redo my factor tree. It's the exact same factor tree in this question. The only difference now is I'm looking for 3 of a kind instead of 2 or a pair. And so looking at the leaves on the tree right above root or cube root of 24, I have 3 of a kind of 2's, and then I have a 3 left over. So that's where that came from. So then I pull out the single 2, and I have a 3 left behind. I get 2 cube root of 3. Moving on to the next thing, I'm going to make a factor tree for 81. 9 times 9 is 81. 3 times 3 gets me 9. 3 times 3 gets me 9. And so that's my factor tree. I'm looking for 3 of a kind. So I have 1, 2, 3, and then I have a single 3 left over. So then my second root is going to be, okay, good, I did it right this time. So my second root is going to become, I have a 3 left over for my 3 of a kind. I put a 3 in front of my root, but I had that 4 already there. And so I need to multiply those two things. So put a 3 in front of my root. 3 times 4 gets me 12. There's a negative in front. So that's where that negative 12 comes from. I got it right once. And then my last root, fortunately, doesn't need to be simplified / can't be simplified any further. So I have 3 like terms now, and I can combine them. 2 minus 12 is 10, plus 1 gets me negative 9, cube root of 3. Now, you get to see it again, we just have variables involved. So I'm going to make my factor tree for 81. We saw it on the previous slide. No shockers here. Break down to get my leaves are 3, 3, 3, 3. I'm looking for 3 of a kind, so I got those, and I have a 3 left over. But what's different about this problem, and I guess the rest of the problem I'm going to go talk through, is that I have variables. And so if I go number by number, which is probably the best way to do it, in my first root, I simplified my 81. I got a 3 in front of my root, a 3 left behind. My second one, I can't simplify the number any further, and that's the same thing with the last one. And so really the only number that gets simplified is that 3. And then what I moved on from there is I looked at the actual variables. So I had 4 x's in my first root. That means I can pull out a group of 3, leaving behind a single x. And I do the exact same thing with the second one because it's 3x to the fourth. So I have 3 x's and a single x left over. And then again, kind of similar to what the previous problem was showing us, I can't really do anything to the cube root of 3, so I leave him alone. So now I'm going to pull out those groups of 3, the 3 of a kind of x's, and I'm going to put them in front of my roots, giving me 3x cube root of 3x plus x cube root of 3x plus cube of 3. And now I have like terms in the first 2 terms. The roots are the same, and in fact, it's even to be more careful, the variables are to the same power, and so 3x times x is equal to 4x. Now, it seems like every example we've seen up to this point, that it's always going to kind of just simplify down to a single root. That's not true, and that's not the case in this one. So even though it seems like I have like terms of a cube root of 3x and a cube root of 3, they're not the same. One of them has an x, one of them doesn't, and so I don't add them, I just stop, which is perfectly fine. Now if we're multiplying, and this should be radical functions, not rational functions, that's something else. And so for multiplying things, it's actually, this is something that kind of belongs to a previous lecture, or so it may seem. If I'm multiplying something like this, I'm going to just do very basic distributive property. 2 times root 5 is just 2 root 5. And then root 15 times 5, root 5, since they're the same root, I can multiply what's under the root. So 15 times 5 is root 75. And now this is where this section comes into play. It seems like I can't combine these any further, but I got to check to make sure. Can I simplify my root 75? Well, I can't. 5 times 25 gets me 75. 5 times 5 gets me 25. I have a pair of 5s. I can put them in front of my root with a 5 left behind. So I'm left with 2 root 5 plus 5 root 5, which is equal to 7 root 5. See this again. In this case, I have 2 binomials. I have to FOIL them out, or distribute, I guess, is technically more correct, but that's exactly what I'm doing. So it seems scary when I did it in one line, but as I talk through it, root 2 times root 6, root 2 times, or negative root 5 times root 6, root 2 times 2, 2 times, or negative root 5 times 2. So that last thing should have a minus in front of it instead of a plus. And now I can't simplify anything further. So root 12 is, oh no, that's not true. I would multiply all of my things out. 2 times root 6 gets me root 12. Root 5 times root 6 gets me root 30. I can't multiply anything in the remainder of my problem. Again, that last thing should have a minus in front of it. It doesn't really affect the problem. And so root 12, I can make a factor tree. 3 times 4 gets me 12, which 2 times 2 gets me 4. So I have a pair of 2s and a remainder of 3. So my first thing will simplify down to become 2 root 3. Now, what I'm going to try to do is on root 30, I'm going to make another factor tree. 3 times 10, and then 2 times 5. Now, it kind of seems like, because this is what we've seen in every example in this section, and I think every example in the last section, that roots will simplify. And if you can make a factor tree, well, then at some point you're going to have a pair, or at some point you're going to have a cube root or something like that, or 3 of a kind. That's not always the case. And so this is a really good example of how we should try and make a factor tree. We should try and simplify it further, but we are unable to do so. So we are just left with 3 times 10 gets me 30, 2 times 5 gets me 10. I don't have any pairs, I don't have any 3 of a kinds, I just have 3 separate numbers. So I can't simplify that guy any further. So I leave him alone, essentially. And so what is the long-winded and kind of unfortunate answer to this question is it doesn't really simplify much further than that second line, which I may have accidentally alluded to. And that's fine. We still have to go through the process. Just like when we have fractions, we should always see if we can reduce. If we have roots, we should always see if we can simplify the roots. But sometimes that doesn't really help us all that much. Sometimes we just have an expression that we've simplified as far as we can. It doesn't look particularly nice, but instead of forcing something that's not there, we just leave it at that point, and that's our final answer. Again, the last term should have a minus in front of it. Doesn't really affect the process at all. Now with this guy, we're going to do a similar process. We're going to FOIL out. So we have root 5x times root 5x, 3 times root 5x, negative 3 times root 5x, and then 3 times negative 3 gets me negative 9. Now what happens here is that if you know your difference of squares, this is a very nice problem because you can just square your first term, which is 5x, square your second term, which is 3, and then it's a difference of squares, so it's just 5x minus 9. So this is a nice case, but it only happens if the first terms on each binomial are matching, the last terms are matching, and then there's a plus and a minus in between. All that being said, if you don't want to do the nice answer, you can just go ahead and go through the process I just did. You'll see that root 5x times root 5x does simplify to 5x, and well, my 3 or positive 3 root 5x minus 3 root 5x actually cancels out, and I'm just left with 5x minus 9.